So this is sort of a very high-level overview about what happens from a product being invented in a lab to the product being produced in the real plant. So from top to bottom, this can be 20 years, 25 years minimum. All right. So first, some scientists or some chemists will have invented this product in the lab. Oh, we can produce this product. This is a new kind of plastic. This is a new kind of polymer. This is a new kind of bioplastic, biodegradable plastic, for example. Okay, so then this scientist publishes a paper on some journal saying, oh, this plastic is a new material that can be used. Then the next phase will be conceptual process design, which is to think of how to produce that plastic in a real scale. Because in a lab, it's very different. You mix reagents together in a beaker or something, and then you get it. In real life, you can't just mix that in the beaker. You need to have a process. All right. And then this goes through maybe some iterations. So maybe test it out in the lab scale, whether this process works. And then you go to a pilot plant, which is like a small plant built in real life, in real conditions, to see whether this process works and whether we need to think about any other considerations that we need to think about. And then there's an iteration process here again until we get the result that we want. So usually this is like 5 to 10 years. It's usually like 5 to 10 years. And once we have the pilot plant works, okay, this product can be produced in real life, not just in the lab. We jump into the next phase, which is the engineering, procurement, construction phase. And this phase, this term is called scale up, meaning that we scale up from pilot scale to commercial scale. The first thing to do will be commercial evaluation, which is like, is there a market for this product? So we want to like really produce it and sell it? Because a product that is good in the lab might not necessarily be commercially viable in real life. Maybe it's too expensive to produce. So after someone decides, okay, this company X wants to produce this product, we go into basic engineering design phase, which is to come up with the PFD, which is the process flow diagram, the PNID, the piping and instrument diagram, and then we come up with the like basic plant layout, how the plant is going to be look like, and so on. Then we go on to what we call front-end engineering design, which is where we flesh out all the equipment in the plant. For example, we need to have this reactor. What's the sizing of this reactor? 5 meters, diameter, 10 meters tall. You have this distillation column. How tall is it? You have this vessel. How big is it? You have this pump. How much power that it needs, and so on. After that, it will go to the detailed design phase where we actually come up with the details of each equipment. For example, this pump. What is the flow rate? What is the head, pump head? What is the manufacturer? What is the motor? What is the voltage supplied to the motor? What is the power requirement? We come up with very detailed information about each equipment in the plant. And then we buy the equipment. We order the equipment, be from China, from US, from Europe, whatever. Then we put them in the plant. We install them inside the actual plant, the site. And then finally, we go to commissioning, which is that we start up the actual plant. And this usually takes about 5 years. Usually take about 5 years, maybe shortest, maybe 3 years, 3 to 5 years minimum. And finally, we operate the plant until, for example, the plant is too old or the product is obsolete. And the operation phase can be 20 to 30 years. So that's how the whole process works. And you can see that your plant design is going to stick around for a very long time. So if your process design is a conceptual phase, it's going to stick around for like 30 years at least. So there are a lot of things, there are a lot of factors that to be considered when starting a process design. All right. So that's how it looks like in the whole industry. And maybe there's a bit too big to be discussed today. So you just go small scale and see what we can do using process simulation. So if we are designing a new process, we can do conceptual design, which is like trying out which process works and which process doesn't. We can use that to do a feasibility study, which is to see like maybe is the cost worth it? Can we sell the product for more than it costs to produce the product, right? Alternative study. So maybe we have 3 different processes to produce this product. Which one is the best? and cost benefit. So maybe from that three processes, we calculate the cost, we calculate the selling price, and then we see which one gives the highest benefit. Okay. Then we can have once a new plant design, once everything is sorted out, we can have process design, which is the upgrade of the conceptual design, preliminary costing, so that from each equipment, we can get the sizing of the equipment, and then we can start to get prices for this equipment. We can optimize the process before we actually build it, because it's easier to optimize the process before you build it than only after you have built the plant, right? Because you don't have to change things. You haven't bought the equipment yet. You can at least make changes before we put down the order for the equipment. If your equipment is already bought and you find out that it's not suitable, then you already paid for it. Maybe it's like a few $100,000 for equipment wasted. And finally, you can run case studies. So for example, if something happens, if the feed changes, what will happen to the plant? So that's a case studies. So if you are in the existing plant, you still use process simulators. You can still do optimization. You can still do debottlenecking. Debottlenecking means that if can I increase the production of this plant? Find out what is limiting the production. Can I make more product than what I'm having now? And then finally, case studies. Same thing. All right. So there are many process simulators out in the market actually. So I've listed like 5 more common ones and like 5 more obscure ones. So the 5 most common ones will be Aspen HYSYS, which is actually the most common process simulator in the world, according to some surveys, right? Which is owned by Aspen Tech. And Aspen Tech also owns Aspen Plus, which is another product of Aspen Tech. Some competitors of Aspen Tech will be ChemCAD by Chem Stations. So ChemCAD is actually easier to use, but has not so many features. And then we have Proto, which is usually used in oil and gas companies. And we have GPROMS, which is by Siemens, and it's usually more for like dynamic kind of simulations. So the top 5 are the like common ones, and the bottom 5 are the more uncommon ones. So someone, I think a lecturer from Portugal, right? He made an open source process simulator called DWSim. So you can actually download it for free and install it on your laptop. Because if you're like using Aspen HYSYS now on your laptop, but you don't realize that actually in real life, process simulators are very expensive. For example, one license, right, for Aspen HYSYS is something around the range of maybe $30,000 per year. $30,000 per year for an Aspen HYSYS license in a real company. Of course, for universities, they actually give you a cheaper price. So DWSim is completely free, and it is quite similar to Aspen HYSYS. So if you know HYSYS, you can use DWSim. So it's like quite similar. And for some more sort of specialized kind of process simulators, we have ICON, which is developed by Petronas Group Technical Solutions, or Petronas GTS. So if you have people working in Petronas, then you will probably have heard of this term, ICON. And this is a Petronas sort of like Petronas proprietary software, which only they have and only they are using. I'm not sure if any other people are using. Schlumberger has Symmetry, which is actually not originally owned by Schlumberger. It's actually owned by another company that Schlumberger bought over. And it's more on upstream applications. So for downstream applications, I try not to use Symmetry. Honeywell Unisim Design. So this is very similar to HYSYS. And finally, you have a HSC Chemistry by Autotech, which is specialized for like mining applications. So if you are mining kind of process or metallurgy kind of process, for example, you are trying to extract iron from iron ore from the earth, this is the best software for you. Don't use Aspen HYSYS. Right. So how do you select the correct simulator? So I have now, maybe I'm a student in the final year. I want to do my plant design project. How do I select my simulator? In real life, right, the first consideration is usually cost, which is the cheapest. But for a student, there's no cost consideration. You just use whatever that you can get on your hands on, right? So the next thing will be application. Each simulator is designed for a certain application. For example, HYSYS is specialized for oil and gas, for refining. and some petrochemicals. Emphasis on some, only some. If you try to use HYSYS for something that is not designed for, like I have a palm oil process, can I use HYSYS? The answer is you can, but your life will be 10 times more difficult. If I have a biochemical process, can I use HYSYS? The answer is probably not, because HYSYS does not have the data for many of the components that you use. So you need to make sure that you choose the correct simulator at the start before you even start doing your project. You don't want to be like, the design project might be something like 2 semesters long. You don't want to be doing something until the second semester, the end of the semester, you realize that your simulator is actually not suitable for the process. And then you don't have time to redo everything anymore. So it's best that you put in some effort to determine which simulator is the best for your application before you choose, right? Because if you have chosen it, you are committed already for your whole design project. So Pro 2, or the name should be Pro/2, if I'm following the name, is also for oil and gas and refining. But Pro 2 has a weakness is that it does not have reactor models. So if I have a reactor, I need to program in the equations myself. So that's the bad thing about Pro 2. But the good thing is that you can have a lot of customization. So like if your reactor is something that is like very unique, you can do it in Pro 2. So Aspen Plus is specialized for petrochemicals and chemicals. So usually if you try HYSYS and it doesn't work for your process, you just go to Aspen Plus or ChemCAD. These are sort of like more common ones, alternatives to HYSYS. And I would really recommend you not to use HYSYS if you are not in oil and gas or refining. If it's not oil and gas or refining, don't use HYSYS. That's the easiest way. So Aspen Plus supports oleochemicals, palm oil, chemicals, electrolyzers, for example, that you might be using. ChemCAD is quite similar to Aspen Plus in application, but ChemCAD has more like solid handling. So if in case your process has some solid powder that you need to do something to it, ChemCAD might be better than Aspen Plus. And if you are like doing some biochemical process, wastewater process, membrane separation process, find out what are the specialized simulators, because the ones in the list probably won't work. They will not work for you. All right. And also, if you have a consideration, find out whether you need a steady state versus dynamics. So 99.9% of the time, your simulation will be steady state. It's very rare if you need dynamics. So usually we just go for steady state. So for steady state, all the simulators above will support. For dynamics, you need to choose between Aspen HYSYS Dynamics or Pro 2 or Aspen Plus Dynamics. That's probably the top products in the market. All right. So tip 0. So I call it tip 0 because this is the tip before you start. Select the right simulator early on. Selecting the wrong simulator can have unintended consequences later on. For example, you don't have this component in HYSYS.